вот еще один день есть. Уже был.
What does the P wave represent? It leads to atrial contraction, but it does not represent atrial contraction.
Depolarization.
Atrial dipole, QRS, ventricular dipole, T, ventricular repole, what are we missing? Atrial repole, which occurs at the same time as the QRS, but there's nothing that represents it. It's being covered up by QRS. We can't see it. First heart sound. Closure of AV valve, second heart sound. Closure of semilunar valve. There's 4 intersecting points where ventricular pressure rises above or falls below another pressure, like here. Ventricular rises above atrial, so what happens here? AV valves close. Here. Semilunars open. Semilunar close. AV open. The time between AV closing and semilunar opening. Isovolumetric contraction phase. Why is the volume not changing? No blood can come in, no blood can go out because all valves are closed. From here to here, closure of semilunar until opening of AV, what's going on?
Isovolumetric relaxation.
Isovolumetric relaxation, no change in volume because all valves are closed. Would it seem reasonable but that the questions I'm asking you right now might be exactly the same questions I would ask on an exam?
Yes.
I think most of the questions that I asked on the last exam I asked in class. Some of them you had ahead of time,
I think
like
this
all
one.
the pre-lab questions for the immune system. About from opening semilunar to closure of semilunar. Ejection. And notice the whole time, the blue line is above the green. Ventricular pressure is exceeding aortic pressure. And that has to be the case for the valve to stay open. During all of filling, AV valve open. Right? So which pressure is lower, atrial or ventricular, to keep the AV valve open? Ventricular pressure. And what keeps ventricular pressure low during this time? It's relaxing. The muscle is relaxing. What keeps pressure high during this time, during ejection? The ventricles contracting. What is stroke volume? Not how do you calculate it, what is the actual number?
17.
70? Okay, how do you calculate it?
120 minus 50.
EDV 120
Minus ESV.
minus ESV 50. 120 minus 50.
That might be too hard of math.
Yeah, true. I'll go back over it. Put together an answer sheet.
No, Mom, I remember how we did the same on Friday. No, I didn't do that.
Preload. So we already covered the intro to cardiac output. You know it's stroke volume times heart rate. It's up here on the board. You also know that stroke volume is the difference between EDV and ESV.
Забудет этот страшный сон.
Now, if you want to increase cardiac output, which you would want to do during exercise, you can do two things. You can increase heart rate, or you can increase stroke volume, or you can do both. And both will increase. And who is single-handedly responsible for increasing both heart rate and stroke volume? And it's doing it by affecting the autorhythmic cells to increase heart rate, venoconstricting to help increase venous return to put more blood into the ventricle during filling, so your end diastolic volume increases, and therefore your preload, which we'll talk about in just a moment. And sympathetic increases contractility, giving you a stronger contraction, so during ejection you get more blood out, less is left behind, reducing ESV. Starting with a bigger EDV, ending with a smaller ESV, really increases stroke volume. Because we're doing both. Not just increasing EDV or just reducing ESV. We're doing both. So big increase in stroke volume. How much can cardiac output go up? What is it at rest? Average. Average person during rest. It's the same as your blood volume. You move your whole blood volume in about a minute. 5 liters per minute. How high can it go? For most of us, yeah, about 25 liters per minute. Trained athletes, 30, 35, maybe even close to 40 liters per minute. What does the trained athlete have that most of us do not? Is it because they can get their heart rates up higher? They have a bigger, stronger heart. So whether it's during exercise or at rest, per beat, they're moving more volume, bigger stroke volume. That's exactly why the athlete's resting heart rate is so low, because they only need to move 5 liters per minute at rest. Their heart rate doesn't need to be very high because their stroke volume is so large. So a low heart rate is a sign of fitness. It means you have a bigger, stronger heart, giving you a bigger stroke volume. Preload refers to how much the myocardium is stretched prior to contraction. So last week I described preload as the load placed on the heart, on the ventricle, prior to its contraction. So if you want to use skeletal muscle as an analogy, biceps brachii. What's the load that biceps brachii has to overcome in order to flex the elbow? The weight of the forearm, plus anything you may be holding in your hand, like a dumbbell perhaps. That's the load. That's the resistance, the force opposing contraction. The heart is a little different, right? The heart's not moving bones like skeletal muscles. The heart is squeezing on a container. The heart muscle is in the wall of a hollow container filled with blood. So rather than moving a bone, the job of the ventricle is to squeeze the blood inside, to raise the pressure, to open the valve to get the blood out. So the way you would load the biceps brachii is to hold a heavier weight, right? So you're going to load it. You're loading it prior to contraction. You grab that dumbbell, and then you contract. And then what you have to overcome in order to flex at the elbow is that load. With the heart, it's a little different. The load placed on the heart before it begins to contract is the volume of blood in it. The more blood you put in it, the more work the ventricle is going to have to do to get that blood out. But then what's the work of the heart once it does start to contract? What does it have to overcome in order to move the blood out through the semilunar valve? The pressure on the other side of the semilunar valve. Right, because we just looked at those pressure gradients, and in order to open the semilunar, we said ventricular pressure has to be greater than arterial pressure. Right, so for the left ventricle, pressure has to be higher than aortic. For the right ventricle, it has to be higher than pulmonary trunk pressure, the pressure on the other side of the valve. That's the afterload. The pressure on the other side of the semilunar valve, the pressure in the arteries, is the afterload. It's what the ventricle is working against once contraction begins. Right? Because it can't move that blood that's in the ventricle out until that semilunar valve opens. With a bigger preload, with a bigger volume of blood in the ventricle prior to contraction, we should get a bigger stroke volume once that semilunar valve does open. We should be able to move out a bigger volume of blood because we started with a bigger volume of blood. So when you increase preload, the whole point of it is to increase stroke volume. And the whole point of that is to increase cardiac output. So think of transitioning from rest to exercise. We're starting to exercise. These are the changes that are going to take place to get that cardiac output up. All right, as the metabolic demands of the body increases, cardiac output has to increase to match. What's actually happening to the myocardium goes back to a mechanism we looked at last semester, the length-tension relationship, or the length-tension curve. Now with skeletal muscles, you are typically within 20% of optimal length. So if I start with biceps brachii as short as I can get it, start fully flexed, maybe it's at 80% of optimal length. Fully extended, now maybe it's 120% of optimal length. Somewhere in the middle, maybe here, at optimal length. And then we can see what that looks like on a graph. And the reason we get the most force at optimal length is because we have the best overlap between thick and thin filaments. Optimal overlap. And therefore the greatest number of cross bridges. So with this optimal overlap, imagine every myosin head sticking out has a binding site on actin that it can bind to. So every myosin head can form a cross bridge. Every time we form a cross bridge, it's followed by a power stroke. And that's what creates force, those power strokes. So if you have more cross bridges, more power strokes, you generate more force, more tension. As you elongate those muscle fibers and pull the thin filaments away from the thick, you reduce the number of cross bridges that can form. Now you've got myosin heads sticking up and there's nothing for them to grab onto. So that's why the tension goes down. Over here, there's some crowding going on. You can see thin filaments are overlapping each other, blocking their own binding sites for actin, for myosin. Fewer cross bridges form, tension goes down. Not only that, once the Z disc pushes up against the thick filament, you can't shorten anymore anyway. That's it. That's as short as you can go. If you can't shorten, you can't generate tension. You can't continue to contract. So we want to be somewhere here with optimal overlap. So skeletal muscles are always within about 20%. Cardiac muscle is a bit different. We're not going to go past optimal length, and we're not going to start at 80% and move towards 100. We're going to start at like 30% and move towards 100. What would be the problem if you were already at optimal length under resting conditions? And then from there you want to exercise. What would be the problem? You can't rely on this mechanism to get any more force out of the myocardium. You're already at optimal length. There's no way to improve. But if you start at 30% of optimal at rest, and then you get closer and closer and closer to optimal, then the contractions are getting stronger and stronger and stronger. Stroke volume goes up higher, higher, higher. Cardiac output does as well because of that. So it gives us a huge capacity for improvement. Well, how do you stretch the myocardium? How do you stretch the contractile cells so that you do get them closer to optimal length? So they're wrapped around the wall of the ventricle. So what do you have to do to stretch? Fill the ventricle with more blood. It's like blowing up a balloon. Right? The more air you put in, the more you stretch the walls. The more blood you put into the ventricle, the more you stretch the myocardium, and the closer you get those cells to optimal length. So as we increase the EDV, which is the preload, so as we increase the preload, we're bringing the muscle cells closer and closer to their optimal length. Now, what do you think prevents overfilling of the ventricles? Why do you think we don't go past optimal length?
Fibrous pericardium.
Fibrous pericardium and the fibrous skeleton of the myocardium. All those collagen fibers within the myocardium, but more